And this is my colleague. So we have many colleagues in the Tohoku University, like these professors, and also we have some colleagues in the University of Tokyo, and Tsukuba, and Ibaraki University, and Tokyo Tech, and Naga Institute Tech. And these are the Japanese institute, but also I have a colleague in university, Dr. Tata Amrila. Until recently, he stayed our group and he was studying the some oxide. I will talk about that. The first, I have two topics. And the first one is Nitrogen square net layered oxide. This is a new superconductor. So, and I will show you what kind of a superconductor is obtained. And the second topic is concerned with rare earth oxide. Probably most of us know that the rare earth oxide is an insulator, but recently we found electrically conducting rare earth oxides. And some oxide is a ferromagnet and some oxide is a superconductors. So I will show you some recent results. The first one is a Nitrogen square net layered oxides. This is a chemical formula, so bismuth oxide or antimony oxide. So this is a crystal structure, so that this is a bismuth or antimony square net. This is a top view, and this is a rare earth oxide layer. So this is a same crystal structure. So in this case, bismuth square net is electrically conducting, and the valence is negative valent. This is an unusual oxidation state. And this rare earth oxide layer is an insulating layer. And this structure is similar to the iron-based oxides, iron-based superconductor, high-temperature superconductors. In this case, this square net is barium 2+. So this is the insulating layer. So, and this layer is iron arsenic layer. This is a superconducting layer. So in a sense, this is opposite. So this part is electrically conducting and this part is insulator. And this layer is an insulator, but this layer is a superconducting layer. And about this compound, previously the Professor Hosono's group reported that this compound is electrically conducting. So if the rare earth is small, so bismuth bond length is shorter and this interlayer spacing is shorter. So in this case, this resistivity decreases with temperature. So this is a metallic conduction. And by changing the rare earth oxides, so for example, the largest lanthanum, this becomes insulator like this. So by changing the type of the rare earth elements, we can control the electrical conduction. This is, in other words, this is a chemical pressure by changing the rare earth oxide, rare earth elements. And previously, this compound was reported to be not superconducting. But after that, we discovered that this compound can be a superconducting by introducing the excess oxygen. So if there is no excess oxygen, resistivity is not zero. But by increasing the excess oxygen, resistivity finally becomes a zero resistance like this. So, and with increasing the excess oxygen, this superconducting transition temperature increases like that. So indeed, this compound is a superconducting, and this is a temperature dependence of the magnetization. And we can also observe the this Meissner effect. This is some proof of the superconductivity. So this compound is the superconductivity around 2 Kelvin by introducing the excess oxygen by using oxygen intercalation. So this is a lattice constant of this compound. The a-axis means correspond to the bismuth bond length. This is constant regardless of the amount of the oxygen, excess oxygen. But about c-axis correspond to this interlayer distance. By increasing the amount of the oxygen, the c-axis increases rapidly. And after that, this compound is superconducting. And this is a p-type conductor, but the whole carrier density is almost constant regardless of the amount of the oxygen. So this is a summary. So this is c-axis length. So c-axis length increases with introducing the oxygen. And at threshold, this becomes superconducting like this. So the longer c-axis lengths correspond to the emergence of the superconductivity. So this compound is a yttrium-2O2 bismuth. And we try to, anyhow, this is a summary of the some representative high temperature superconductors. So for example, this is a perovskite copper oxide. So in this case, in case of the X equals 0, this is an anti-ferromagnetic insulator, but with doping the strontium, this is a whole dopants. So, and finally, this compound becomes a superconducting. And in this case is a nitride chloride layered compound, this one. In this case, a pristine compound is insulator, but by introducing by intercalating the lithium metal, resistivity decreases and the superconductivity appears like this. And in this case, this is Y2O2 bismuth. In this case, there is no carrier doping. So excess oxygen is not related with the carrier doping. But by introducing the oxygen, c-axis increases and finally superconductivity appears. So this compound is a little strange because the superconductivity is induced by not carrier doping like this compound, but the increase of the c-axis length. So this is just a geometrical change of the lattice constants. Anyhow, this bismuth square net superconductivity this is observed for the first time. So there are the various bismuth square net compounds, but some of them are not superconducting. There are some superconducting compound. This superconducting emerges because of the palladium bands at Fermi level. So we tried to make other layers compounds by using the similar method. So in case of the yttrium-2O2 bismuth, this oxygen intercalation is very easy. So by introducing the Y2O3, amount of the Y2O3, we can introduce an excess amount of the oxygen. And this is easy, but for other layers, oxides bismuth, this is not applicable because excess oxygen is difficult to be introduced in these compounds. So we use calcium oxide as a new oxidant. So this is indeed a strong oxidant. And by mixing the calcium oxide, this calcium oxide oxidizes this compound by introducing excess oxygen, and the calcium metal is gone by the evaporation. This is schematically shown in this figure. So the calcium oxide is used for the oxygen intercalation for the various layers to oxide to bismuth. So as a result, we can succeed in oxygen intercalation in various Re2O2 bismuth. So this is a summary. So this is the temperature dependence of the resistivity of R2O2 bismuth. So this is a pristine R2O2 bismuth. In this case, terbium-2O2 bismuth. So this is not superconducting, but introducing the excess oxygen, this becomes this is a zero resistance. So this is a superconducting. In case of the dysprosium, this is also the superconducting by oxygen intercalation. And this is yttrium. So yttrium is in pristine state, superconducting below 2 Kelvin, and this superconducting transition temperature increases by oxygen intercalation. And also these erbium and lutetium, the superconducting transition temperature increases by oxygen intercalation. So interestingly, this terbium and dysprosium and erbium and lutetium, this is not lithium, but these are the antiferromagnetic compounds in pristine state. So in such a magnetic compound, the superconducting temperature is significantly decreased, but as you can see, the TC, superconducting transition temperature, is the same as other compounds such as non-magnetic Y2O2 bismuth. This is at present, I don't know what's going on, but this is some interesting properties of these compounds. And this is a summary of the superconducting transition temperature. Superconducting transition temperature is always around 2 Kelvin by oxygen intercalation. And for all of these compounds, the C-axis length is different, but by oxygen intercalation, the C-axis length increases. And finally, the superconducting transition obtained like this. And this is shows an interesting feature. So this is a C-axis length, but this is a C-axis length divided by the A-axis length. So this is a kind of the aspect ratio of the unit cell, or in other words, this is the tetragonality of this compound, of the unit cell. So for all of these compounds, at the threshold of the same threshold of this tetragonality, the superconductivity emerges like this. So if C over A is over 3.42, the superconductivity emerges like this. So this superconductivity is more or less a tetragonality induced superconductivity, not carrier induced superconductivity. And this is one exception. This is a no superconductor. This lanthanum-2O2 bismuth, this lanthanum is the largest ion, so the bismuth bond length is longer, and bismuth square net and interlayer spacing is the largest. So as a result, this is a semiconducting or insulating conduction. But by conducting the oxygen intercalation, the C-axis increases, but this resistivity decreases like this. And this is not superconducting, but this is highly electrically conducting. So, and this whole mobility is relatively high. So this is a not single crystal, but polycrystal, but this for mobility is relatively high in comparison with other oxynuclide or oxycalcogenide. These are the oxynuclide and oxycalcogenide polycrystals, various polycrystals. And this is a mobility, carrier mobility, and this is a hole density. So most of them shows high hole density but low mobility. But this compound shows high hole mobility. This is comparable with host compound of the iron-based superconductor. So this compound, some of this compound is superconducting except for lanthanum, but this lanthanum CO2 bismuth also interesting from the viewpoint of the electrode materials. And previously we performed the oxygen intercalation by using the high temperature, such as 1000 degrees or something. And this high temperature sintering often resulted in formation of the impurity phase. So we were looking for the some more efficient oxygen intercalation method at lower temperature. So this is one of the low temperature topographic oxidation method. We use this zirconia doped cerium oxide as a solid state oxidant. So we just sinter this compound and this compound. This is separately placed in same quartz tube, and we heat this compound and this compound in a quartz tube. So this is some XRD pattern of this compound and picture of this cerium doped this zirconia. And above 200 Kelvin, this compound is changed more or less. And as a result, the oxygen is supplied from the cerium doped zirconia to this compound. And finally, we can obtain this compound, excess oxygen in this compound. And this is a result of the superconducting transition temperature. So in the previous method, we use 1000 degrees sintering temperature, but by using this solid state oxidant, we can increase, we can obtain the superconducting Y2O2 Bi from above the 200 degrees C to 800 degrees C. And by using this method, we can obtain high pure superconducting compound like this. So anyhow, this is also known as oxygen storage material. And this compound can be used for the solid state oxidant at low temperature oxidation. And this experiment is related, concerned with bulk polycrystal. And also we tried, we performed the oxygen intercalation, but also we tried to dope lithium or fluorine or hydrogen in place of instead of the oxygen. So lithium is indeed intercalated in this layer, and fluorine and hydrogen substitute the oxygen like this. This is fluorine ion and hydrogen ion this is an anion. And as a result, we obtained also the superconducting Y2O2 Bi. This is not oxygen intercalation, but lithium intercalation or fluorine or hydrogen doping. And actually, we can obtain a higher superconducting transition temperature in case of the lithium intercalation on the hydrogen doping. So in this compound, the oxygen intercalation is not necessary factor to obtain a superconducting emergence of the superconductivity. And still this tetragonality dependence seems to be applied for this emergence of the superconductivity. So this is all these results is experiments of the bulk polycrystal. So next we try to make a epitaxial thin film of this compound by using the pulsed laser deposition. Pulsed laser deposition is this is some starting materials, and by irradiating a pulsed laser, then we can evaporate this starting materials, and finally we obtain the thin film, epitaxial thin film. In this case, as I told you, this bismuth is unusual valence. This is a 2- ion. And so by using this method, always we obtain not this compound, but the bismuth, trivalent bismuth of the Y2O3. This is also the very stable compound. So anyhow, it is difficult to obtain a negatively divalence bismuth by using this pulsed laser deposition, even in ultra high vacuum. So we developed a different method. This is the first generation solid phase epitaxy. So at first we feed bismuth and yttrium powder, and the bismuth powder and yttrium powder react each other. And after that, the secondary we feed this bismuth yttrium powder and this amorphous Y2O3 on calcium fluoride substrate. This is a single crystal substrate. And finally, we obtain Y2O2 bismuth epitaxial thin film. This is the XRD pattern of this thin film, and XRD peak is very small. So this means this crystallinity is not so sufficient. And after that, we developed a multi-layer solid phase epitaxy. Now, this is a starting compound. So by using the sputtering, we made a multi-layered precursor. This is Y2O3, and this is yttrium, and this is bismuth. So that this is a multi-layer of the bismuth and yttrium and Y2O3 layers. After that, we hit this multi-layer inside. And as a result, we can obtain the Y2O2 bismuth epitaxial thin film. And this is XRD pattern. So in comparison with the previous method, we can obtain much higher crystalline epitaxial thin film of this compound. So we obtained this epitaxial thin film. So in comparison with the bulk polycrystal, this Y2O2 bismuth shows higher electrical conduction because this is a single crystalline. Although this epitaxial thin film doesn't show a superconductivity. So this is similar to the pristine Y2O2 Bi. Probably there is no excess oxygen in this compound. And also we try to make a similar antimony square net compound. So in this case, we can successfully obtain this epitaxial thin film. So in the previous report from a different group, bulk polycrystal was reported. This is highly insulating conduction. This is conduction is almost very small. But by making the epitaxial thin film, we can obtain a highly conducting LSO2 antimony, this compound, like this. So the resistivity is 4 order of the magnitude or 5 order of magnitude different. This shows a much lower resistivity in comparison with the bulk polycrystal. So the reasons are not so clear, but this compound is known to form the charge density wave. Charge density wave is one main reason to be insulating. So it is possible that this is epitaxial thin film. So by from the epitaxial force, this formation of the charge density wave could be suppressed. Anyhow, this is probably the first report of the highly conducting the antimony scarlet compounds. So next, we would like to move to the different compound. This is a very simple compound. This is a binary compound and rare earth oxide. But this is some of them is new solid phase, and some of them are some interesting properties. And in this case, this compound is only thin film, epitaxial thin film, because this is a metastable phase. And by using the epitaxial force, such a metastable phase can be stabilized on a single crystal substrate. This is a schematic of the pulse laser deposition I told you. So this is a ultra high vacuum chamber, and this is a starting materials. And by irradiating ultraviolet strong laser, this is a ultraviolet laser. So this photon energy is very high. So in a temperature scale, this is 60,000 Kelvin or something. So by focusing the X-ray laser, many compound is easily evaporated like this. And finally, we can obtain a thin film. And for thin film growth, we also use the infrared laser for heating. This is a very convenient method to obtain a high temperature, such as 1,000 degrees Celsius. And so this is some photograph of the evaporation. So this is a invisible laser, ultraviolet laser, and this is a evaporated species from the starting compound. This merit of this method is it is possible to obtain metastable compounds because this is not thermally equilibrium state, but a kinetic state. And also there we can obtain highly pure thin films because this is ultra high vacuum. So this is a very old story. So for example, this is titanium oxide. For example, the anatase type titanium dioxide is very famous for the photocatalyst. But by using the pulse laser deposition, we can heavily dope the cobalt. Cobalt is some magnetic ion in this TiO2. And this cobalt is heavily doped, but this is not this cobalt doesn't form the impurity phase, but this cobalt is solved in the titanium dioxide. So in other words, cobalt substitute the titanium site like this. And this is a trans TEM image, so atomic release of the TEM image. And this cobalt doped titanium dioxide is shows a very, very high Curie temperature. This is more than 500 Kelvin, and the maximum is 600 Kelvin. So this is very high in comparison with other well-known ferromagnetic semiconductors. And this is a semiconductor. So by using the field effect, we can increase the paramagnetic state to the ferromagnetic state. This is an anomalous Hall effect. And this corresponds to that by applying the electric field, this magnetization increases from 0 to finite. And this is a first demonstration of the electrically induced room temperature ferromagnetism. And next, we move to the recent topics, rare earth oxide. This is well-known rare earth oxide. This is a chemically stable rare earth oxide. And most of them are denoted as R2O3. For example, the gadolinium 2O3 and dysprosium 2O3 and holmium 2O3 or something. And these are the, most of them are paramagnetic or anti-ferromagnetic at very low temperature, or some are diamagnetic. And most of them have a very large band gap. So this is a band gap is a very large, so that this is highly insulated. And this is chemically stable and almost no magnetic and wide gap and high dielectric, high permittivity insulators. And on the other hand, today we talk about the rare earth monoxide. This is not R2O3 but RO in a chemical formula. Many years ago, some compounds are reported. This lanthanum and cerium and praseodymium and neodymium and samarium monoxide. This compound synthesized by using a high pressure synthesis. And this is the bulk polycrystal. And after their report, no study has been reported. And this European monoxide, this is a very famous ferromagnetic semiconductor. So the single crystal and the epitaxial thin film can be obtained. And this ytterbium monoxide, this was reported to be some polycrystal or polycrystalline thin film has been reported. And this compound is metallic conduction. And for example, about the yttrium monoxide, this was known to be a gas phase. This is a gas. And in this plume, there is a yttrium oxide gas molecule. This is not solid. And the other rare earth monoxide also they are known to be only a gas phase. And this is a Y2O3. This is a stable compound, and this is a Bix byte structures, and this is transparent because of the wide band gap. And this is completely insulated. And this is slides previously I showed you. This is a Y2O2 bismuth thin film. But during this experiment, we found that some amorphous Y2O3 becomes not transparent but black. There is, of course, no black Y2O3. So I thought that there is some new compound in this amorphous Y2O3 thin film. And after some investigation, we found that this black yttrium oxide is yttrium monoxide, like this. This is the first solid phase of the yttrium monoxide. This is also the epitaxial thin film on the calcium fluoride substrate. So this metastable compound is stabilized by epitaxial force from this substrate. The starting material is a Y2O3, but by using a pulse laser deposition, we obtained the yttrium monoxide. And this is a rock salt structure. This is a transmission electron microscope image. This is rock salt structure. And we also performed the X-ray fluorescence photography. This is very useful for the element selective structural studies. And we found that this yttrium, divalent yttrium forms rock salt structures. So anyhow, this is a first rock salt yttrium monoxide, and this yttrium is divalent like this. This is a XPS spectrum, and this there is some mixture of the trivalent yttrium, but this divalent yttrium is a majority. And this yttrium KH is in between the yttrium metal and Y2O3. So this is a signal of the divalent yttrium. And as I show you there, this Y2O3 is transparent, but this yttrium monoxide is not transparent like this. So this means that the band gap is very small. This band gap is about 5 eV, but this band gap is about 0.1 eV. And by changing the amount of the oxygen vacancy, so by increasing the oxygen vacancy, the resistivity decreases. This is representative properties of the some ordinary oxide semiconductors. And this resistivity is much higher than the resistivity of the Y2O3. So this is a conducting yttrium oxide. So after that, we extend to synthesize various layers monoxide. So next one is a cerium monoxide. This is there is a one 4F electron and one 5D electron. So in this case, this is a photoemission spectra, and cerium 5D orbital and the 4F orbital shows some strong hybridization. And this compound shows metallic conduction like this. And at very low temperature, the Kondo effect is observed. So interestingly, this whole carrier shows a very high mobility, more than 500 mobility. And also at low temperature, the electron carrier appears. So that this is close to the semi-metal. So this is a heavy fermion paramagnetic compound. And the next praseodymium is also the metallic compounds. And this compound shows also the Kondo effect, and different from cerium monoxide. This is weakly ferromagnetic compounds like this, and the Curie temperature is about 28 Kelvin. Although the ferromagnetic hysteresis is very small. We can observe that both ferromagnetic magnetization and anomalous Hall effect. And another one is a neodymium compound. So this is a 4F3 configuration. So with increasing the 4F electron, the ferromagnetic ordering is the strength. So this is also metallic compounds like this. And this shows clear ferromagnetic hysteresis and anomalous Hall effect like this. And the Curie temperature is 19 Kelvin. This is still low. But this Curie temperature is much higher than the neodymium chalcogenide or nictide. So this is a neodymium nictide and chalcogen. This is an insulator, and only a neodymium nitride shows a high Curie temperature. And neodymium monoxide shows also the higher Curie temperature in comparison with this compound, and this is ferromagnetic. And also this is a samarium. And this is a non-magnetic, but this is a heavy fermion system. This is also metallic conduction. And in this case, there are other samarium monochalcogenide, sulfide and selenide and telluride. These are the semi-conducting because the band gap is large. And for this compound, by applying the external pressure, this compound becomes a metallic. This is called as a golden phase. But in case of the samarium monoxide, oxygen is the smallest anion among them. So this smallest oxygen contribute to the chemical pressure in this compound. As a result, the samarium monoxide becomes metallic without external pressure like this. And this also shows a Kondo effect. So that this compound is also the heavy fermion system. And this compound is predicted as a wild semi-metal, but at present, I don't know this is a wild semi-metal or not. So next in periodic table, the next element is europium, but europium monoxide is a famous compound. So the next element is a gadolinium. This is also the 4F7. This is half-filled 4F orbitals plus a 5D electron. So in this case, interestingly, so europium monoxide is a 4F7 5D0 configuration. In this case, the Curie temperature is 69 Kelvin. But the gadolinium monoxide shows a much higher Curie temperature. This is 270 Kelvin. This is much higher than the europium monoxide. And this is a summary of the Curie temperature of the various magnetic semiconductor. In case of the diluted doped magnetic system, Curie temperature is relatively high, but this is a diluted system, so the magnetization is usually small. In this dense ferromagnetic semiconductor, so for example, europium sulfide and monoxide and gadolinium mononitride, this magnetization is large, but the Curie temperature is low. But the gadolinium monoxide shows a much higher TC in comparison with other dense ferromagnetic semiconductor, and this is comparable to the TC of this diluted doped ferromagnetic semiconductors. So this is a very interesting compound for the spintronics, semiconductor spintronics. And recently, we reported terbium monoxide. This is more than half-shelled ferromagnetic semiconductors. And this Curie temperature is very large, similar to the gadolinium monoxide. And in this case, this temperature dependence of the magnetization shows strange behavior. So this is a Curie temperature. So at Curie temperature, the magnetization increases. And the magnetization monotonically increases, but around 20 Kelvin, the magnetization rapidly increases like this. So probably this is caused by the emergence of the magnetic sublattice of the 5D spin around here. And around here, this corresponds to the emergence of the 4F magnetic sublattice of the 4F spin. So probably this is a superposition of the temperature dependence of a magnetization like this. Such behavior is often observed in iron garnet. Garnet contains layers at A site and iron at B site. So the different atoms shows different magnetic sublattices based on the 4F magnetic sublattice and the 3D magnetic sublattice. But in this case, only single telebeam atomic site shows formation of the magnetic sublattices of the 5D electron and the 4F electron independently. This is an interesting magnetism of this compound. And this is recently reported the chromium monoxide. This is 4F10 configuration. So this compound shows good electrical conduction, and this is electrical conduction can be tunable by changing the amount of the oxygen. So this is a kind of the oxide semiconductors. And this Curie temperature is also the relatively high, 130 Kelvin. And this study was performed by the Dr. Tata Murira of the University of London. And about ytterbium, ytterbium is almost nearly free occupied 4F orbitals. And in this case, this is non-magnetic, but this shows good electrical conduction, and this is oxide. This is also the one of the oxide semiconductors, and this mobility at room temperature is relatively high. So this ytterbium monoxide is epitaxial thin film and simple rock structure, so that this compound can be used for also the electrode compound. And lutetium oxide, this is a 4F free shell monoxide. This is also the oxide semiconductor. And the final one is this lanthanum monoxide. This is no 4F electrons, but 5D1 electron. This is a new superconductor. This is a resistivity, and the resistivity becomes 0 at around 4 Kelvin. And this superconducting transition temperature can be tunable by the electron density of this compound. And this superconducting transition temperature is much higher than lanthanum monochalcogenide. This lanthanum telluride 1.4 Kelvin, and lanthanum selenide 1.0 Kelvin, and lanthanum monosulfide 0.8 Kelvin. So this is a chemical trend. But this lanthanum monoxide, this is a chemical, from this chemical trend, lanthanum monoxide should show the lowest superconducting transition temperature, but this lanthanum oxide thin film shows the highest superconducting transition temperature. This is some irregular chemical trend. And all of these layers monoxide is rock salt structure like this. This is very simple. So for example, this superconducting lanthanum oxide can be epitaxially grown on a European monoxide epitaxial thin film. This is a ferromagnetic compound. The magnetization is very large. So even only a 2 nanometer or 6 nanometer European monoxide almost destroy the superconductivity of this lanthanum monoxide because this is a ferromagnetic semiconductor possessing the very strong magnetization. But anyhow, these heteroepitaxial structure can be used for the platform of the superconducting spintronics. So this is a summary of the second part. This is a very stable rare oxide, R2O3 or RO2. This is a almost non-magnetic and completely insulators. But rare monoxide in this study, this is a metastable phase with a divalent rare ion. This is an unusual balance. And some of them are reported previously many years ago, or only gas phases. But all of these compounds can be grown on rare earth monoxide like this. So this red one is a new solid phase, and these are the superconductor or semiconductor or ferromagnetic semiconductor also, or ferromagnetic metal. So it is very interesting. So in this case, by changing the 4-electron number, the physical properties are not so changed. But in case of the rare earth monoxide, by changing the 4-electron number, the physical property changes very, very significantly. Some of them are superconducting, some of them are ferromagnet. So these are promising electronic magnetic materials. So this is a final slide. So there are various new metastable compounds and new metastable functional materials can be unveiled or discovered by developing the novel chemical approaches. So today, the first one is a superconducting R2O2 bismuth. This superconductivity is discovered by adding oxygen or other elements. And also by using the novel solid phase epitaxy, we can obtain highly conducting antimonadic square-net compounds. Also, by using the epitaxial thin film growth, we can obtain first single crystalline or first solid phase rare earth monoxide. This is an interesting compound as magnetic or electronic materials. So thank you very much for your attention.